So this is Module 5. We're going to look at combinations and compositions of functions. Now we're going to see combinations is going to be basically combining two functions with either addition, subtraction, multiplication, or division. We'll start with that. Composition is putting one function into the other function. So we're going to see where we'll have the outside function, and inside we'll have another function being the input. So those are the difference between the two. So as we see, combinations involve addition, subtraction, multiplication, and division. Now when we have division, of course, since one function ends up in the denominator, an issue we're going to have is we're going to have to make sure that we exclude any values from the domain where that denominator function could become 0 or does become 0. So we will look at domain with this situation. Most of the others we don't have to worry so much, but let's just look at a few examples. We'll see that the first two is really just combining like terms, but let's go ahead and take a look. Sum and difference of two functions. So we're going to work with these two, and let's kind of color code them. So we'll do the first function, f of x, and that sort of red, mauve color, burgundy color, and we'll do the second one in blue. Okay, so we're first define the sum. So let's go ahead and do that. So that's going to give us g of x again in blue, x again in the burgundy. Okay, so we're going to write the first function. I'll put parentheses around them to kind of to indicate that they are each separate, different functions. So there's one function, and then the operation we're doing with them is we're going to add them together. Second function, 9 minus 10x. Now with addition, since addition plus, when we multiply by positive one, nothing changes. The signs all stay the same. So in this case, we're actually able to go ahead and remove the parentheses. I'll show that that's happening. The plus sign just kind of attaches to the 9. Negative 10 is still going to be negative 10. So addition is kind of like the easiest one to do. And then we're going to come along and we're going to combine like terms. So x squared, there's no other x squared, so we'll just write that down. There is this 5x, but then there's a negative 10x, so we have to combine those two. 5 and negative 10 combined becomes negative 5x. Okay, and then we have the numbers. We've got a negative 8 and a positive 9. When we combine those two, we end up with a plus 1. And so that's our final answer. We've combined this function. Now subtraction is very similar, but a little different at the same time. So we've got our g of x function, we've got our f of x function. Oops, didn't change on me. So we've got our f of x. So this time we're going to take the two functions and we're going to subtract them. So we write the first one, and again I'll put a parentheses around it, x squared plus 5x minus 8. Second one we're going to say is 9 minus 10x, that's the g of x function. But this time if we remove the parentheses, now the first one there's nothing in front, so nothing worried, just like the last one. But what we're going to need to do is to make sure that this negative distributes through the parentheses on the second one. Okay, and so we're going to, as we take off the parentheses, this is going to become minus 9 plus negative so positive 10x. Okay, so that's how that's affected. The front polynomial is not affected. X squared plus 5x minus 8. And again, all we're doing is combining like terms. So there is no other x squared term, so that just goes there. There's a plus 5x, and this time a plus 10x, so we combine those to become 15x, positive 15x. And now we have a negative 8 and a negative 9, so that's going to be negative 17. And so notice the difference in the answer and the need to distribute through that negative. A lot of times students will just not use these parentheses, which is fine as long as you remember that as you write down this back one here, that you distribute through that negative sign. And then all will be just fine. Multiplication of two functions. So we're given two functions here, little different ones. We're told that they're defined for all real numbers of x, and so their domains is everything. And what we need to do now, again, let's go ahead and do one as a red function, one as a blue function. We're going to multiply them, so we get 4x minus 6 times x minus 5. So it's, since we, in this case, we have two binomials, what we're going to want to do is multiply these two binomials, again, using FOIL, first, outer, inner, last. Or you could do it with a vertical. Let me show you that one. So you could practice out your FOIL, or you could just list this as 4x minus 6, and then vertically underneath go x minus 5, and go ahead and do the multiplication, maybe like we did in 3rd or 4th grade when we got two-digit number multiplication. Right? We take each of the bottom ones, so I'll take this 5, we multiply it times negative 6, negative 5 times negative 6 is going to be plus 30. Negative 5 times 4x is going to be a negative 20x. Then we deal with the x's, so we're going to take x times negative 6. Now remember when we did two-digit multiplication, we indented one, so we'll go ahead and do that. The nice thing about this is it lines up the like terms. So x times 6, or negative 6 is negative x, or negative 6x. And then we take x times 4x, and that'll give us 4x squared. Then we add straight down, we get 30, we get negative 26x, and then we get 4x squared. And you'll see if you follow the FOIL, the first, the outer, the inner, and the last, that's basically what we did, and you'll get the same answer. Okay, so that's multiplication. Again, nothing that we haven't done before, but maybe it's just we're seeing it differently, listed as g of x times h of x, okay, using function notation. Quotient of two functions, this is actually one of my favorites because it's really so easy. We're given two functions and we're asked to find their quotient. So again, we'll go ahead and use some color coding. The thing that makes it so easy is most of the time we're going to have functions that don't really reduce. So all we end up doing is writing out the numerator, x squared plus 5x minus 8, fraction line, the denominator, 9 minus 10x, and we're done. Because they don't, there's no canceling going on, there's no reduction. I guess you could see if these will factor, the top one would factor, but it's, even if it factors, it's not going to factor into 9 minus 10x. I can tell you that much right now. So we're all good with it. That's our final answer. Could make it all in one color if you wanted to. But one thing we do have to do here, because it's not completely easy, is we have to state its domain. In most questions, they will ask us, well, here's a quotient, what is the domain? So the domain is going to be any number in the x value, but the one thing we can't have happen, we cannot let 9 minus 10x be equal to 0. So we solve this, and that's what we're going to exclude. Let's just go ahead and subtract 9 from both sides. You could add 10 to both sides if you wanted to. but and then to finish this off, we'll divide by -10. And so we see that whenever x is equal to negative positive 9/10, uh, well, we're going to have to take that out of the domain. So then we could list the domain as everything else. Again, from -infinity. See if I can. Infinity sometimes a little difficult for me to do until we get to positive 9/10. I'm going to exclude that. I'm going to union to the other side of 9/10, and then we're going to shoot all the way to positive infinity. So that'll be our domain. Okay, that's really combinations of functions: addition, subtraction, multiplication, division. And now we're going to take a look at the last operation we're going to do in this section is composition of two functions. And this is where one function goes into the other. Think of it as like a factory. Maybe you're building cars. Typically in a car factory, they don't make all the parts. They import a lot of the parts, like a steering wheel. So, but there is a factory somewhere making steering wheels. So that could be like a function. There's that one factory is to make steering wheels. That steering wheel becomes an input into the assembly line to actually make a car. And that's what's going on with the composition of two functions. You have two processes, and one becomes, there's an input of one, the output of one process becomes the input for the next process in the line. So one function is the input of the other function. So we write it as f composite g. So this little symbol here means composite. Some people will read that as fog, right? F-O-G, but it's not really an O. It's a composite sign. So, and order is important. Sometimes we're putting F into G, and so that would appear as. I guess I'll just do it. I'm not sure where else I have printing, but you could also do G composite F of X, and again, that's going to be a different way around. So the order that things are done is critical. You could definitely end up with different answers. Okay, so let's see what our example is. Clear this out a little bit. So that was the word composite. We don't really need it sitting there. Take that out. And so we have our two functions. And again, color coding is helpful. We'll stick with our maroon and our blue. And so to composite these two together, what we're going to do is we're going to take back here. The outside function is going to be f of x, so that is going to contain the g of x function. Okay, so as we set this up, what we're going to do is we're taking the f of x function, and that's the outside function, so we'll rewrite it as 3x squared minus 6. So everywhere there's an x, we're going to put a big open parentheses. And then what are we going to put into there? Well, we're going to put the function g of x, which is this part here. So square root of 4 minus x. And that's the composite. And so in a way we're done, but they also say, simplify as much as possible. So as we look at this, the square root and the 2, we square the square root, which means we get following order of operations. Let's change over to here. Is that the square root and the square cancel with each other, so we're left with 4 minus x minus 6. We distribute through the 3, so that gives us 12 minus 3x minus 6, and then we can combine this, the 12 and the negative 6, so we're going to get negative 3x plus 6. I guess you could put it in the front if you want. So that would be the composite of it. Now we want to be careful here though, because it looks like because of the answer we've arrived at, that our domain would be all real numbers because we could plug any x value in here and we're just fine. But notice that the first input is g of x. Does anyone see any issues with this first function? So x is first going to go in here. Before it gets squared, it's going to be in here. So really, we need at this point, at this particular factory, they can't have this inside part be less than 0, right? They can't have it be negative. So 4 minus x has to be greater than or equal to 0. It has to be non-negative. So again, if we get the domain question here, we always want to be thinking ahead. So now I'm going to just show you, usually we'd subtract 4 and then divide by -1, but when you divide by a negative with an inequality, you have to remember to flip the symbol. So one way I came across, making it a little bit easier for me so that I don't have to worry about forgetting about that kind of stuff, is I will actually add the x to both sides. I don't have to worry about multiplying by a negative. And so then we're going to get that 4 is greater than or equal to x. Now, sometimes this is hard. What side is the x on? So let's do a number line. The boundary point is 4. So there's 0. 4 is like over here. 4 is included. X lives in the side that's smaller than 4. X has to be smaller than 4. So what that gives us is x has to be over here. And so that's going to tell us this is negative infinity. So we're going from negative infinity until 4. 4 is included. So that's going to be our domain. Even though the final answer could take any value of x, the first input of x goes into a square root, then that number gets squared. If you've got an imaginary number, remember, when you square it, it's still going to be imaginary, so it's not real. But if we need real number answers, we've also got to be thinking of the domain. Now, if the question doesn't ask about domain, okay, you're free. But I want you to at least think about it. Every time when you have a composition of function, you've got to make sure not just that the answers domain is going to work, but that the input function. Now notice I really didn't have to worry about the output function until the end. So we kind of take care of it that way. And we're going to actually directly address that in the next example. Okay. Well, actually, after this one. So this one comes from, and I think we only have you doing one of these questions. It's a little more difficult because you're actually working backwards. We've got the answer, it's like Jeopardy, but what we want you to do is find what were the two functions, right? What was f and what was g, so that when we made the composite, we ended up with 4x to the 6 minus 5. The thing is this is something we need to do in calculus because oftentimes when we are either taking a derivative or integrating, which you'll get to those in calculus, sometimes we need to know the pieces that a function is made up of. Now, one thing is there may be more than one correct answer, but they do not want the identity function because all of these could be said, well, oh, one function is x, y equals x, and then this is the other one, and plug in x, and you got it, right? So one answer, we could say f of x equals 4x to the 6 minus 5, and then g of x equals x, you plug x in there, and that works. Yes, f composite g is that function, but that's like, that would work for everything, so it's not real helpful. So what we want is to look at a slightly different, is there something else we could make as the inner function? Well, we could go with, say, like this, that this is the input, and then 4 input minus 5. So the outside function in this case, we would say is 4 f of x equals 4x minus 5. What are we going to put in that x? Well, we're going to put a function which we will call g of x, and we'll call g of x x to the 6th power. And notice when you take this composite, let's go with f of g of x, and we take 4x minus 5, and then we put the x to the 6th power in here. Now there's not much to do, but we end up with 4x to the 6th minus 5. So we end up back where that's what they're calling h of x. Okay, so that works. There's another way we could have done this. We could have looked at, kind of erase this part. We could have put a parentheses and say, okay, this whole thing here is an input. And so it's x minus 5 is the outside function. We could define that. And so then the inside function is going to be 4x to the 6. And now when you put this in for x, we're back to where we started. You could try it out. You'll see that one in the notes function as well. It is a little bit of challenge. It takes a little bit of thinking, a little creativity, because again, you're going backwards. But it is a good skill to start building up on. So this is the last one. Definitely looking at the domain of a composition of two rational functions. Now what we're going to see here is, since we're doing f composite g, so f is the outside function, g is the inside function. We're going to do the composition this way. Now, since the inside function is g of x, we from the beginning, that first place x is going to get put is into this function. So we have to make sure that whatever value we use for x does not give us division by 0. So we will say, okay, x, that can't be 0. So we're starting, and again, there's nothing to solve for here because it's already solved. X is equal to 0. So we'll really remember that's what we have to exclude. And I know I misspelled this earlier in the, I think I left off the C or something in an earlier module, but I didn't want to go back and fix it after I saw it. So x equals 0, so we're going to exclude that. Now what we're going to do is we're going to do this composite, which is going to get a little complicated, but that's okay. So we're going to take the f function, 4, and then the x we're going to replace by a parentheses, minus 3. So 4 over x minus 3 is what we start with. Inside this parentheses, we're going to put the function g of x. So that's 11 over x, and that's what we have. Now, they're going to ask us, let's see, simplify your answer as much as possible, right? So what does that mean? Well, it means that it's not very comfortable to see a fraction and a fraction, complex fraction. So what we're going to do is we're in a couple different ways we could approach this, but we're going to multiply this by x over x. And the reason is because when we distribute this bottom x through, x divided by x is 1, so we're going to get rid of the fraction. So it's because the x is a denominator. Okay, so we'll go ahead and do this. In the numerator, we just end up with 4x. In the denominator, we end up, I'm going to show this, when we multiply, this x has to multiply here and here. So we get 11x times x minus 3x. And as you see, the reason we did this is x divided by x cancels out, becomes a factor of 1. And so what our simplified function becomes is 4x over 11 minus 3x. And now we ask the question, what value of x, if we put in here, would create a 0 in the denominator? So again, we've got part, we know that we have to exclude 0 up here. Let's go ahead and do this. And so we're going to need to take this one and we have to see what else has to get excluded. We can't let x be such that it would make this 0. So again, we could go either way we want. I'll subtract 11 from both sides. When I've got an equal sign, I'm not too worried about it. When I've got inequalities, I'm a little bit more concerned. So minus 3x equals negative 11. And then we're going to divide both sides by negative 3, just solving for x, right? This cancels with this. Negative over negative is a positive. So what we find is that we need to exclude x whenever it would become 11 thirds. Now 11 thirds would work in g of x, right? Up here, 11 thirds is okay, but if we put in that 11 thirds, by the time we're done, it's going to get us a division by 0. One way or another. Okay. And so what's our domain? So we'll draw a number line. Here's 0. Okay, so we got to look out for 0. So we're going to exclude 0. That's gone. And 11 thirds, where is that? Well, let's see, 12 thirds would be 4. So it's just a little bit less than 4. And again, we need to exclude it. And what we're going to do is we'll draw it out. So x can be anything else that way, there, there. So again, we've got negative infinity at this end. We've got infinity at this end. So we can go from negative infinity to 0. And then we're going to go from 0 to 11 thirds, and then we can go on. So what the domain looks like in this case will be negative infinity to 0, exclude 0, and we can go from 0 to 11 thirds, exclude 11 thirds, and then we can go from the other side of 11 thirds all the way to infinity. So this would be our domain. Again, a complicated way to write it, but if you do it out on a number line, it could be very helpful. So that brings us to the end of looking at some examples that will help us through the Module 5. That's our direct instruction. Now's your time to complete the learning activities. Remember, anytime you need assistance, we've got the online tutoring. We've got instructor office hours. Please come and see us. We're lonely out here. We're happy to work with you. When you come to office hours, we also learn what's going on in the course. So please do come and take advantage of our office hours. It lets us really get the enjoyment of teaching. That's why we all became teachers, right? And then also working with your peers through the discussion forums. And again, your teachers are there too. They're going to be looking at those. So those are the ways to do it. Good luck, and we'll keep moving forward.